It was a usual day at work on Friday, September the 4th, 2020. I was working on improving our RBI generator, Tapioca, reviewing some PRs and responding to emails when a colleague pinged me on a PR. Request times have gone from 100 to 250 milliseconds, and a single Sorbet signature seems to be the culprit. I need to investigate this. At the time when this PR was opened, I'd been working with Sorbet for about a year and a half. We'd adopted Sorbet on our main monolith at Shopify that we call core, and had fine-tuned the runtime impact to decrease some of the overhead coming from the Sorbet runtime component. We hadn't gotten any similar reports about a runtime slowdown like this. It was hard to believe that this was because of Sorbet. So I noted down my suspicion in the PR and we waited to see if deploying the PR was going to bring the performance back. Lo and behold, after a couple of minutes, Bassam ran a profile on the deployed version of the code and we had our old performance back. The stack traces were clearly implicating Sorbet. But before we dig further into that, let's talk about Sorbet first. Sorbet is a gradual type checker for Ruby that is built as a static executable in C++. The type signature annotations of Sorbet are by design Ruby code. You add a sig method call with a block to declare the types of your method parameters and return value. This allows Sorbet to stay pure Ruby. There is a small cost though. We need the sig method to be defined by someone at runtime. Otherwise, Ruby won't know what to do with that method call. tsig is the module that defines the sig method. It is defined by the Sorbet runtime gem. Having a runtime component allows Sorbet to do more things than it can do with the static type checker. Since Sorbet is defining the sig method, it can actually use it to validate the type signatures at runtime too. This is very useful to ensure that the types that a method declares are actually the types that are being passed to it at runtime. Maybe your method expects an integer, but someone is sending it a string instead. Since Sorbet is a gradual type checker, this method call might not be statically analyzable. The runtime component, though, can catch this case if you have tests that cover it. The signature definitions wrap your method calls and check the types. But how does this runtime magic work? How can Sorbet runtime associate a sig method call with the method that follows it and then instrument the method so that it can check the parameter and return types? Enter the magic of method added. In Ruby, the module class has a method called method added, which, if defined in a module or class, is called whenever a new instance method is added. This method is passed the name of the method that is being added, using which we can do many interesting things. Using that, we can build our own toy tsig module that we can call toysig. We need to first implement the sig method. We can just store the current sig block in an instance variable and be done here for this simple implementation. Now that that is done, we need to know when a method is added to our module. Let's add a method added method on our module for this. This method will do nothing if there is no signature defined currently, since we don't want to intercept all the methods, just the ones that have a signature. Now, let's get a reference to the method object for the method that was just added using the instance method. And now we're ready to replace the method itself. We use define method to replace the method. We grab all the arguments, the keyword arguments, and the block that are passed to this method. The first thing we'll do is to evaluate the signature block. The signature block is evaluated very late, since it might have references to classes or modules that are not yet defined at the time the signature is declared. By evaluating it as late as possible, we make sure everything can be resolved. Since this is a toy example, we won't do much with the signature. We can just print the arguments and the block that was passed to the method. Cool. Now we need to call the original method. For that, we will use the bind call trick. Using our method object from before, we can bind that method to the current self and then call it with the arguments, keyword arguments, and block that was passed to our replacement method. We will store the return value in a variable and print it to the screen. Finally, our replacement method needs to return the same value as well. That's our toy signature module done. Let's see how we can use it. We can define a toy shop class that we will use like this. Let's add a constructor that takes some parameters and prints in initialize. Let's also add a method that takes a block and yields to it. We can also add a method without a signature to ensure that we never replace that method. Let's see what output we get from this. As expected, we see 2 calls to initialize and 1 call to the with method. And we see that the signature block is evaluated when the methods are called and can access the actual arguments and block passed to the method. The original method call still goes through, and we can also intercept the return value before returning it from the method proper. So this explains why the method got so much slower after the addition of a signature, right? Well, no. Since the real Sorbet runtime implementation has some escape hatches that we've been using heavily to optimize the runtime impact of all of this. We can't get rid of the method wrapping completely because of some technical reasons, but we can completely get rid of type validation, and we can even perform signature block evaluation at an earlier time in our Rails application. Those 2 techniques actually ensure that the impact of Sorbet runtime in production is minimal, while still providing value in development and test. So who is killing our performance if all of this is true? The profile points to the method added method, which looks suspicious. Let's see if we can dig into what is happening here. I start most of my investigations by adding puts statements into relevant places. Where better to add that than the actual method added hook added by the tsig module. Here I'll use my favorite tool of running bundle open Sorbet runtime to open the source of the currently installed version of Sorbet runtime in my editor. That way I can make changes to the source code of the gem and run my application to see the changes. Let's navigate to the location where the method hooks are added and add puts, self, and method name to see when this method is being called. Going back to our shop model, we can see that we have the extend tsig and the signature that was removed in the PR. So we can experiment with this. In our application, we can change the eager loading behavior by setting the eager load environment variable in development. This ensures that I get a behavior as similar to the one in production as possible. I also want to disable Spring so that every run is a fresh one. I use the disable Spring environment variable for that. So running Rails console with these environment variables gives me a lot of output from the put statements during eager loading of the application. Now that we've booted our application, we can get rid of those. Shop.fetch1 seems to run just fine and doesn't even trigger any method added hooks. So what's going on here? Let's take another look at the fetch method on shop. There's some conditional logic depending on if shop current is set or not. Our initial call was done without setting shop.current. Okay, what happens if we set shop.current to the first shop? So far, so good. Let's call shop fetch1 again. Whoa, what happened there? What are all these methods? And how many of them are there? Let's copy them over to a text editor so that we can analyze them more easily. I'm going to use the Rails runner to run this command and then pipe it to a clipboard copy operation. Now that we have it in our text editor, we can analyze these calls. This is crazy. We get about 1,600 calls to method added when we called shop fetch 1. Each of these calls is doing some processing to match itself to a signature and do some other checks. If each one of these calls takes about 10 microseconds to process, and if there are about 6 calls or 8 calls to shop fetch during a single request, then that would more than explain the 150 millisecond performance hit. It seems we found our immediate source of the problem. But why is this happening? We need to go deeper. Let's take a look at these methods again. These are all class methods defined on our shop class that are triggering method added hooks when the shop instance is cloned. But also notice that the class name that is printed is not shop. This is an anonymous class that is getting methods added to it, since it obviously has no name. But which class is this? Also, why are class methods triggering method added method? Should they not be triggering the singleton method added method? Okay, let's see if someone is doing something fishy between the time we call shop clone and the time method added method is called. For this, I will use my favorite trick of adding a binding pry with a global conditional so that I can control when the binding pry is called or not. With that in place, let's start our application in the same way again and see what happens. Okay, our application has booted, and because we haven't set the global variable yet, it hasn't printed anything or hit any breakpoints. Let's fetch the first shop again and just clone it this time because we know the problem is with clone. No need to keep hitting the fetch method. Before we do that, however, let's flip our global debug switch so that we can break inside the method added call. Here we are. So what is our backtrace? Who has called us? There might be some shenanigans happening there. Backtrace in pry will give us that information. It seems we're being called directly from kernel.clone. No one seems to be adding these methods manually, so where are they coming from? There was also something fishy about the class instance when inside this method. So let's see what self is. Well, that's also weird. This looks like the singleton class of a singleton class. There's something deeper going on here. Where in Rails were all the callback methods being added from? Who was triggering them? I reached out to the person that best knows the internals of Rails, Rafael Franca. We had an hour-long pairing session with Rafael where I explained the situation and showed him what was going on. His initial instinct was that this looked like the model body was being re-executed when clone happened. Seeing as all the methods that were being added were things like before save xxx or after save xxx, we dug into the internals of active support to see where those callback methods could be added from. So we went into the Rails codebase. First stop was looking at the definition of def has many. This is a simple method that doesn't do much other than call another method. Let's dig into builder has many.build. We see that that class inherits from builder collection association, which in turn inherits from builder association. And voila, here is the build method. Reading the code, we can see that it is doing a few things, and one of them is to define callbacks. This is what we're interested in. Where is define callbacks method defined? We need to go down the inheritance chain again, back to collection association. Here is the define callbacks method. And it calls define callback for each type of callback it needs to register, which is then creating methods formatted like callback name underscore for underscore name. Bingo! This is exactly what our methods look like. So how are these methods defined? Using a class attribute call. From here, we dug into how class attribute works. One thing that we discovered about the writer of a class attribute is that it always redefines the reader when the value is set. So if someone was setting a callback while the clone was happening, we would have the callback method redefined, which would trigger the method added hook. We tried to figure out if that was what was happening, but that was not what was happening. So we really didn't know what to check next. As we were looking at how collection association was calling class attribute, Raphael realized that it was generating instance predicate methods and accessor methods unnecessarily. So he quickly added a commit to Rails to fix that. Moreover, we realized that it was not just methods registered by class attribute, but basically any class method defined on the shop model that was being added during a clone. At this point, we were out of ideas of how Rails might be affecting the cloning of an active record model. So Raphael suggested that the problem could be in our app code. We decided it was a good idea to add a very lean model in our codebase to see if we can replicate the behavior with that, and finished our pairing session. So that's what I went ahead with. I created a foo model on our application. Since our application has custom sharding logic that we call podding, it was a little tricky to add a simple model, but after defining two simple methods on the model class, I was good to go. I went ahead and added a method with a signature on it and a class method for good measure, and tested the same clone operation with an instance of this model. I can't recreate the same behavior on this model. Even the class method is not triggering method added during cloning. What is different? The big guess was that this model was not using our custom sharding code. Let's see if that changes anything. Let's add an include for the sharded table module. Now, let's try doing the clone again. Let's enable the breakpoint again. And let's try cloning the first foo instance. Wow, this time the behavior is the same as shop. So it must be our potting code that's doing something fishy here. So let's make sure that that is the case. Let's comment out the sharded table include and try it again. Enable our breakpoint, try the clone. Wow, the behavior is different. Where to go from here now? So one way of troubleshooting this is to go to the source of the sharded table implementation. The sharded table does a few things. It registers a class attribute called hasShopData, and then it registers the model on the shard, and then it includes some other modules into the model, which does some class eval and adds some callback methods. And it also has some checks, and there's also a class methods module that gets mixed into the active record model. So one way of troubleshooting this is to try to comment out the methods partially. I call this binary search within the source code. So if we keep doing this with the runner and enabling the breakpoint and doing the clone, we can actually see if we're ever printing the weird method added hook hits. So if we comment out everything, we obviously don't hit anything. If we only leave the class methods extend line, we don't have the weird behavior either. Now let's try just adding the class attribute. Okay, no weird behavior still. And now let's register the model on shard and let's see what that does. That does an include and a register. So let's comment out the include. Okay, no weird behavior. And now let's comment out register. Okay, so it seems the problem is in base.include. Now let's dig into that. So that has an included method that does a class eval, and that class eval registers a before create and an after find. Let's see if it's the class eval that's problematic. Run the runner, no weird behavior. So it's obviously not the class eval. Let's see the before create. No weird behavior, so it's obviously not before create either. And now, finally, let's try after find. The moment after find is in place and is running on the model, we have this weird behavior with the method added hooks. What is going on here? So let's try this. Instead of including the sharded table, if the problem is with after find, let's just register an after find callback method on the model. That should trigger the same behavior, right? Okay, let's try it. And voila, yes, that triggers the exact same behavior. Now our model is isolated enough from the application that we can put together a reproduction script. So one way of doing that is using the bug templates inside of Rails. So Rails has a bug template for the active record gem, which is a self-contained script that uses bundler inline and initializes active record, defines a few tables, declares their active record models, and then runs a test with them. So let's use that as a base for a small script that we can put together so that we don't have to deal with our application code ever more. If we just run this, we can see that it does a few things. It prints all these SQL statements, and it runs the tests, and all the tests pass in their default form. Let's analyze how this bug template script runs. First of all, it uses bundler inline and defines a gem file inside of the script. and then it requires active record, mini test, and then initializes an active record connection using SQLite. It then defines a schema, defines two classes, and then defines a mini test class that runs a single test. We don't need that test, and we don't need these post and comment models. Similarly, we're not going to use these tables either, and we are not going to use mini test because we just want to run our script and see the behavior. We also don't need the active record based logger because we don't want to see the SQL output, because active record isn't what we're troubleshooting here. So we will create a schema that just creates a shops table. We'll create a class shop. And instead of bringing in Sorbet runtime, we're just going to add our own method added hook here. The rest is the same as the foo model that we had. Now let's create a shop instance and let's find the first shop and clone it. Afterwards, let's do a shop.afterFind, and then let's find the first shop and clone it again. This is our script. This should be able to show us the weird behavior that happens after registering the after find callback. Here's the schema again, and here's the shop model again with the method added hook inside, and a class method and an instance method. Like I said, we're creating the shop model, we're finding the first shop model and then cloning it, and then registering an after find callback, and then finding the first shop model again, and then cloning it. Okay, let's see what we get when we run this script. So we're creating a shop model, that's fine. We're doing the first clone before registering after find. Okay, we don't hit the method added hook. We register after find and do the second clone after registering after find, and then we hit our method added hook. So this is the exact same behavior. We're able to reproduce this in a very small script. But how could after find be affecting clone? In order to understand that, let's take a look at the clone method. So the clone method produces a shallow copy of the object that's given. The instance variables of the object are copied, but not the objects that they reference. And there's also a discussion about the difference between clone and dupe on the documentation of dupe. And the difference seems to be that they have different semantics in descendant classes. So clone is used to duplicate an object, including its internal state, but dupe just uses the class of the descendant object to create the new instance. When using dupe, any modules that the object has been extended with will not be copied. Okay, that's good information to know, the difference between dupe and clone. Let's look at how dupe operates inside of the MRI codebase. It first finds the class of the given object, and then it allocates a new instance of it and calls it dupe. And then it initializes the copy, and then it calls an init dupe method on that, and then it just returns that duplicate instance. This method is super simple. Now let's take a look at clone. Let's see if we can figure out how that's implemented. There isn't much here. It seems to call a mutable obj clone. Let's see if we can find that in the Ruby code base to get a better understanding of what it does. Let's search for all lines that start with a mutable obj clone. That usually gives you the location of where the functions are defined in the MRI codebase. So that seems to be at 446 in object.c. And here's the method. So similar to dupe, it also seems to find the class and allocate a new instance of it, but then it does something different. After doing that different thing, it does an init copy, and in our case, it calls an id init clone function and does some freezing thing and returns the clone. So really, the only big difference between clone and dupe is this block here. And that block seems to be calling an RB singleton class clone and attach method. So this might be related to singleton classes, right? That's interesting. If this is related to singleton classes, then we need to figure out who's allocating a singleton class. One way of doing this, and this was a trick that was told me by Alan Wu that you'll see later in this video, is to use the object space trace object allocations block. When you set up an object space trace allocations block, what it does is it traces all the object allocations within that block, and then you can ask the object space to tell you where certain objects were allocated from. In our case, we want to see if the singleton class of shop was allocated. By asking object space.allocation source file and giving it the shop.singleton class, we can get the file, and similarly we can get the source line, and we can print it to the screen. Okay, now with this, let's run the script again and see what happens. Okay, it seems the singleton class is being instantiated inside of active support callbacks, inside a method named makeLambda. Again, let's put a put statement in there, and let's see what we get back. Running the script again, now it will hit our puts line. Here we see that a call send is being made on an active support callback conditional value, and also an instance exec is being made on a shop instance. And it's given a proc that's defined on test RB line 55. But that's exactly the block we passed to afterfind. So let's see what instance exec does. We know what instance exec does, but let's see how it works internally. Oh, there you go. See, it creates a singleton class for evaluating the block. So it must be the case that afterfind runs instance exec, which then in turn creates a singleton class. And it seems that makes all the difference between clone and dupe. Now, given this knowledge, we can actually get rid of all of active record in our reproduction script as well. We can make our shop class a simple Poro class. It doesn't have to be an active record. And then we can create a new instance of it, and we can try cloning it first. And then we can call .singleton class on shop, which will create the singleton class on a shop instance if it doesn't exist yet. And then we can try cloning it again. Now, if our hypothesis is correct, when we run this script, the fact that we created a singleton class should make a difference between the first and the second calls to clone. Let's see if that's true. Yes, it really is true. It seems the second clone does hit our method added hooks. What is a singleton class exactly? Let's see if we can figure that out. A singleton class in general is a way of giving some behavior to a single object and not the general class that it inherits from. So if we create two instances of shop, named shop and shop2, and then if we create a singleton class on shop, and then define a method named hello on it that just puts world, then we should be able to call the hello method on shop. It works. But when we try to call the hello method on shop2, it doesn't work. Even though the class of shop and the class of shop2 are exactly the same. They're both shop. We were able to add special behavior to the shop instance, but not the shop2 instance. Now let's try to see if we can understand how singleton classes work by trying to understand how Ruby represents these things. We will start small. We will first define a shop class with a single instance method, and we will create an instance of that shop class called shop. Now, when we ask shop for its superclass, it should be object. And when we ask shop for its class, it should be the class. And when we ask the shop instance for its class, it should be shop. And similarly, if we try to get the list of instance methods on shop and just on shop, then we should get the name method. This is the simple case. Now let's switch it up a little bit. In this case, we will create the same shop class, but we will also define a class method on it called fetch. Defining a class method actually defines that method on a singleton class of the shop class. If we try to look at the properties of the classes and the objects, we can see that the shop superclass is still object. The shop class is still class though. So Ruby hides the fact that the shop points to its singleton class, which in turn points to the class. But if we ask the shop for its singleton class, we can get a reference to that singleton class. But we need to ask explicitly. Also, if we ask shop for its instance methods, we get the name. But if we ask shop's singleton class for its instance methods, then we get the name fetch. And this is how class methods work. Class methods are actually defined on the singleton class of a class. Now let's make this a little bit more complicated. Now let's have the same case that we had before with the shop class that has a name method and that has a fetch class method. We also want to create an instance of this shop. But now we want to create a singleton class on this shop instance. In this case, the superclass of shop is still object. That doesn't change. The class of shop will always be given as class for us because Ruby hides the singleton classes in the normal case. But if we ask shop for its singleton class, we can get a reference to that class of shop. And if we ask the shop instance for its class, we get shop. And if we ask the shop instance about its singleton class, we get the reference to the singleton class as well. If we also ask shop for its instance methods, we expect to find name in there. And similarly, if we ask shop's singleton class for its instance methods, we expect to find the fetch method there. Finally, we can also ask the shop instance's singleton classes instance methods. Because no methods are defined on that, that just returns an empty set. We can also try to find the superclass of the shop's singleton class, and that is shop. And that's how singleton classes actually delegate the methods that are not defined on them to the actual shop class. Now let's make this even more complicated. We will define a singleton class of the singleton class of a shop instance. We have the same shop class with the same instance method name and the same class method fetch. We create an instance of this shop and call it little shop. and we create a singleton class of this little shop and a singleton class of that singleton class. Now let's see what the superclass of shop is. As expected, that's always object. The class of shop is again hidden from us, its class. We can still get a reference to the singleton class that's between shop and its class, and we can still get a singleton class of the small shop instance. But we can also get a reference to the superclass of the small shop's singleton class, and that's shop. And we can also get a reference to the small shop's singleton class's singleton class and ask it for its class. That's also class. But we can also ask it for its superclass, and that is the singleton class of shop. Given this understanding, let's try and figure out how cloning should work. And let's start with the simple case that we had. This case is simple. When we want to clone the shop object, then the clone is just a copy of the shop object itself, because the clone can also point to the same shop class that the shop object points to. There is nothing more to clone here because the behavior will be shared between shop and the clone. It is a similar situation for the little bit more complicated case as well. When we clone the shop object, we just need to create a copy of the shop object itself. Because they both share the shop class, even though the shop class has a singleton class, because the shop class is not being cloned, there is nothing more to clone. Just creating a clone of the shop object is enough, just like the previous time. The third case, where the shop object has a singleton class, is a little bit more complex. Now, we need to clone the shop object itself, but because the shop object has specific behavior in its singleton class, we also need to clone that singleton class along with the clone and attach it to the clone object as well. Now, both the clone singleton class and the shop singleton class will share their superclasses and their classes as shop and the shop singleton class, respectively. That won't change, but we will have to be creating an extra clone of the singleton classes as well. If we don't do that, then the behavior of shop and its clone would have been different. But we don't want that, so we want to clone the singleton classes as well. Now let's take a look at the most complex case, where we have the singleton class of the singleton class of shop object created. In this case, it's actually very similar to the previous one. We not only need to create a clone for the shop object, we need to also create a clone for the shop object's singleton class. But now also the shop object's singleton class's singleton class needs to be cloned as well. Notice that each singleton class is attached to the object that it is a singleton class for. This ensures that only that object can access those singleton class methods and call them. But this wasn't exactly how things were working inside of Ruby. So after pairing with Alan Wu from the Ruby core team for about 2 hours, we were able to have a reproduction script that shows how singleton class being defined on an object causes the cloning to be imperfect. Here we create a very simple class foo with a single class method, and then in the case 1 we create a new instance of it and then clone and compare. In case 2 we create a new instance of it, add a singleton class to it and clone and compare. In case 3 we create a new instance of it, create the singleton class, and add a method on it, and then clone and compare. Clone and compare does something really simple. It just reports the original object singleton class versus the clone singleton class, and then also the original object singleton class versus the clone singleton class, and reporting only prints the instance methods. Now this gives the following output. For case 1, the object singleton class instant methods is empty. So is the clone. And so is it for the singleton class. For case 3, they also match. But for case 2, where we only have the singleton class defined, we can see that the singleton class instance methods are different. The clone somehow has a foo method. So case 2 is surprising because the cloned object has different contents to the original. It is surprising that the clone singleton class has the method foo, whereas the original object's singleton class didn't. So this is the PR we created with Alan after a couple of hours of work, trying to understand what's going on inside of the RB singleton class clone and attach method. That was, if you remember, the only thing that was different between dupe and clone. Now it turns out that this method as a guard was trying to see if the given class was a singleton class or not, and if it wasn't, it was just returning it. But the check wasn't enough. Not only did we need to check for it being a singleton class, but we also needed to check to see if it was attached to the object or not as well. If it wasn't attached, there was nothing to clone, and if there was nothing to clone, there was nothing to attach either. So we created this PR, and we got a few comments on it for clarification. After a minor modification and some improvement in the code comments, the PR was finally merged on the 17th of November 2020. As a result, the fix is now in Ruby 3.0. Just 8 days ago, the fix was also backported to the 2.7 line as well. Now let's see if we can use our diagrams from before to understand what exactly was going on inside of Ruby. So if you remember, this was the problematic case. The problem with this case, when Ruby was cloning, was that Ruby is following the class pointers. So when Ruby clones shop, it creates the clone object. And then it follows the shop object's class, and it finds that there is a singleton class there. So it clones that singleton class, because singleton classes need to be cloned. But now, when it follows the class pointer of the singleton class, it finds the singleton class of the shop class. And mistakenly, Ruby thinks that because that's a singleton class, it needs to be cloned as well. But that singleton class doesn't belong to this singleton class. That singleton class is attached to the shop class, not to the singleton class of the shop object. So it really shouldn't have been cloned. But if it does get cloned, then the clone actually gets the class methods that were on shop. Because the thing that is being cloned is the singleton class of the shop class. So then the clone has the fetch method on its singleton class's singleton class. And that creates the difference between behavior between the clone and the shop object. And that was the root cause of our problem, because those were the methods that were getting added to that cloned singleton class. And every time those methods were getting added to the cloned singleton class, we were getting a penalty in our application. Now let's see this fix working on Ruby 3. First, let's make sure that we still have the unexpected behavior in 2.7. We do. Let's change Ruby to 3 and run the script again. And we don't have the unexpected behavior. Our investigation is done. Now we can relax.